I'd like to welcome all of you here tonight. This has been an astounding week. The mail trucks were going left and right tonight with all the tax returns that they're trying to drop off to the post offices. We, of course, this week saw Condi Rice deliver a series of many lectures to the 9/11 committee. And, of course, Easter Sunday. Easter Sunday was also a very special event, especially in the movie industry, because once again, The Passion of Christ surpassed the #1 movie last week, which was Hellboy. And you kind of think about it, it's kind of funny. But in seeing this, that The Passion of Christ had risen to the top of the charts again, it got me, like it does many people sometimes, thinking about God. And I thought maybe we'd talk a little bit about God for the next few moments. I know all of you are saying, what in the world is he talking about? I thought we were going to Saturn. See? Stick with me. Because the funniest thing, I was in Beth Israel the other day, and I was reading a People magazine in Spanish, and which meant I was going really slow. And I heard an older lady sitting next to me saying, you know, the good Lord never gives you more than you can handle. But the lady next to her was kind of flippant. She said, yeah, unless you die of something. And I thought, that's kind of interesting. And then I'd read somewhere that God is not dead but alive and well, currently working on a less ambitious project. And then it reminds me of the quote by Lenny Bruce, every day the people are straying away from the church and going back to God. I think the quote by Napoleon was very interesting. Religion is what keeps the poor from rising up and murdering the rich. But I think when we talk about God, I think this is apropos. The world today is absolute proof that God is actually a committee. And I got to thinking about this. If I were God, what would I do? What would I do? And I got very serious for a moment, and I realized the first thing I would not do is send another flood, because, you know, with the realization that the first one was useless, I would look for other projects to become involved with. And I wouldn't certainly be as flippant as my uncle used to be at Thanksgiving dinners, when he would sit there and he would fix us with that eye of his, that stare, and he would say, I think everyone should believe in something. I believe I will have another drink. But if I were God, and I found throughout all of my creation, I had a world that had a species that occasionally demonstrated intelligence and logic and curiosity, and a technology with the capability of building instruments that could extend their sight beyond their small little round world with very close horizons. If they could look out beyond, I think I would be tempted to put something out there for them to take a look at through those telescopes. I think, first of all, I'd put a very stable star out there for them, so they wouldn't be bathed in gamma radiation, X-ray radiation. They wouldn't have solar flares that would wipe them off the surface of that planet. They'd have a little bit of time to develop their technologies, their sight, their realization, their understanding of the universe around them. I think one of the things I would do is, because the sun would be in their daytime sky, I would put something really big in their nighttime sky. I'd make it really bright colored, something nearby like the moon, that they could look at and see these huge craters and mountains and devastation that have been racked on this world, but changed on their own. It had been erased, almost forgiven on their own world with the process of erosion. I think I would put something very close to them that would spur them on to go there, to take a look at it, to extend themselves out within their own environment. That would be a pretty good idea. I think maybe if I was feeling a little philosophical and deep, I'd put a world next to them, a world enshrouded with clouds, but incredibly hot. It would be a world where the greenhouse had run amok, and just letting them know, be careful of the technologies that you have, because it could happen here. Then I think if I had a little spare time, I might put a smaller world to the opposite side of them. A world that maybe once had oceans and rivers and streams and clouds and rainbows, but now was cold and barren. So they would appreciate their own world. You know, it would be kind of fun being God, placing these things in the sky for these creatures to take a look at. I think what I might do is maybe put a big, gigantic one of these objects out there, frozen cold, beautiful stripes and bands going across it, little servant moons moving back and forth. It would be a cosmic minesweeper, so this planet that these creatures were living on wouldn't get hammered by asteroids and space junk constantly coming in. It would absorb them for them. It would become their grand protector. That'd be a cool idea. You know, every once in a while, if things got slow, I'd send a comet by. Something with a huge tail that would just brighten their sky, change what they were thinking, stop them for one moment to take a look at it, and let them look up with awe and wonderment as it passed by. That would be a really good idea. But you know what I think I'd love to do the most? I would like to create something of such astonishing beauty, especially against the black backdrop of the deep cosmos, something that was so amazingly beautiful, it would hang in their skies like a jewel, something that every time they looked at it with their telescope, they would say, wow. Wow. Even if they'd seen pictures of it, they would say, it's really real. And you know, I'd go a step further. I'd give it rings. I give it beautiful rings, 3 separate rings that you could see through your little telescope. And sometimes they would cast shadows on that world, and sometimes they would turn edgewise and totally disappear, just to reappear again later. That would be a really cool thing to do if I were God. Do you know what else I'd do? I would look high and low, across the world. I would find someone, maybe a young girl, living in the Bronx. And what I would do, when she went to Cardinal Spellman High School, I'd make sure she had a telescope. Because when she looked through that telescope, the connection between her brain and her heart, this would become her first cosmic connection with the universe. That'd be a good idea. When she picked up her bachelor's in physics and astronomy at the State University of New York at Stony Brook, I would make sure she made her way out west, towards Caltech. There, she would be taken in with the Voyager 1 team, and for that moment in time, this young woman would see the rings of Saturn in a way that no other human beings had ever seen before. Oh, heck, let's crank it up. After she got her doctorate, I'd have her join the staff at the University of Arizona. I'd have her become an invited member of the Voyager 2 team, and what she would do is unravel the mysteries of minor rings around Uranus and Neptune. That sounds like a fun idea, doesn't it? To have that power, that capability. But then about 1990, I would make sure that she became the leader of the Cassini camera team that would build the most sophisticated camera that had ever flown in outer space. I would make sure that as she became the leader of this team, that she would encounter some problems, some politics, and oddly enough, she would even have contact with the lady, with the image that Jodie Foster played in the movie Contact. She would parallel some of those same problems in her life. And then, about 10 years ago, she wouldn't know I was God. We would happen to run into each other at Caltech, right in the middle of a NASA JPL program to decide the roadmap through the solar system, where, coincidentally, that very same day I was so lucky in meeting this young person, Stephen Hawking would run over my foot with his wheelchair in the cafeteria, and he would say, "Good night." And I would feel so lucky because I would know that 10 years later, I could bring her here to sunny Boston and invite her to share with us absolutely one of the most exciting space adventures human beings have ever undertaken. That's what I'd do if I were God. And tonight, if I were, I would say, I would like to present that woman to you, Dr. Carolyn Porco.
That was the most brilliant introduction I've ever heard. And are there any questions? Actually, I have a serious question. Is that counted against my time? I have an hour from now? Okay, anyway, well, thank you very much. What more can I say? My God. I'm delighted to be here, and I'm delighted to be able to talk to you about an enterprise that has been 13 and a half years in the making, that I personally am extremely passionate about, that has tremendous historical and scientific significance, and that is now only finally a few months away. And it is so significant that I think it deserves some historical context. So let me digress for a moment and tell you that back in 1958, the committee that was advising our nation on matters aeronautical and missile technology and so on, it was called the National Advisory Committee on Aeronautics, was discontinued, and in its place arose the National Aeronautics and Space Administration, NASA. And in its infancy, amazing that a government institution could do something so wise, it articulated a very bold and far-reaching plan to undertake the exploration of our solar system. And this plan called for a three-phased approach to exploring the planets. And I want you to think, this is back in 1958, they were thinking this far ahead. This has always amazed me. First, this plan called for reconnaissance missions. And as you know, the space program was born of the military, so the language still exists. Reconnaissance is a military term, but reconnaissance missions are these missions that were sent out in the 1960s and in the 1970s to briefly visit a planet, just fly by, gather as much data as could be gathered on the passage, and then relay that back to Earth. Second phase called for orbiters, where an orbiter was put in orbit around the planet so that the whole planetary system, its atmosphere, its magnetic field, if it had such, its moons, its rings, and so on, could be monitored over a long period of time, and interactions among all these systems could be monitored. You could call this the systems approach, if you will. And this was the second phase to gathering as much information as we could about our solar system. And then finally, the third phase, again, back in 1958, was sample return. After we had gathered enough information about a planet, we could actually go to it, pick up a piece of its surface, if it was a solid body, perhaps scoop up a bit of its atmosphere, if it only had an atmosphere, and bring that back to Earth. And the reason being that seldom are spaceborne, in fact not yet, are spaceborne instruments capable of making the kind of measurements and the precision of measurements that we're capable of making in Earth-based laboratories. Anyway, the Voyager 2 spacecraft, both of them, the Voyager spacecraft, launched in 1977, that was nearly 20 years after NASA was formed, were part of that plan. They were the first reconnaissance missions to the outer solar system. And for those of you who were paying attention, or those of you who have bothered to go and read up on what the Voyagers have done, they basically taught us what the solar system is comprised of. They were epic in their scientific sweep and in what they were able to accomplish in their decade of touring the outer solar system. But they were step one. The exploration of the planets, to me personally, is the grandest of human endeavors. It is the signature enterprise of our time. It is what we in the late 20th century, early 21st century will be remembered for. And it has seen the most extraordinary of humankind's achievements. And in just 11 weeks to the day, we will witness another remarkable achievement when Cassini is placed, the Cassini spacecraft is placed in orbit around the planet Saturn, beginning phase 2 in our exploration of the Saturn system. Cassini at that point, will be the farthest robotic outpost, stationary outpost that humankind has ever established in our solar system. It will be 10 times farther away from the sun than the Earth is. And conditions at Saturn, as has been already mentioned, are very alien indeed. Temperatures are colder than minus 300 degrees Fahrenheit, a little bit colder than in this room. The solid objects that are there are made of water ice and not rock, and water ice behaves very differently at temperatures that low than it does here on our planet. Sunlight is 100 times fainter than at Earth, so broad daylight on Saturn is like early twilight here on Earth. Arriving at Saturn will be like entering the realm of an alien planet alien planet orbiting a distant star in another quadrant of our galaxy. That is really how adventurous and how adventurous this mission will be, and how alien Saturn and its environment is to us, and how different it is compared to the warm and comfortable conditions we know here on Earth. For us scientists who are jazzed about planets, it's going to be a singular moment indeed, because Cassini is outfitted with the most sophisticated suite of scientific instrumentation that has ever been carried into the outer solar system. And with it, we will be able to conduct in-depth investigations of everything that is Saturnian. Why Saturn? Why is such an ambitious program aimed at the planet Saturn? Well, it is because out of all the planetary systems that are directly available to us for study here in our solar system, Saturn, with its complex interacting systems of atmospheres, magnetic field, and moons and rings and so on, is an ideal destination for study of many of the same physical processes that we believe occurred in the formation of the solar system, or that are important for present-day dynamics of our solar system and, in fact, of planetary systems around other stars. So in studying the Saturn system, we have the opportunity to study a very broad spectrum of scientific questions reaching well beyond Saturn itself. And so I'm going to take you through the various elements of the Saturn system this evening. I'm going to mention what questions remain to be answered after the Voyager flybys, and what we hope to find out with Cassini. This is the Voyager spacecraft, the Cassini spacecraft. It is the largest planetary spacecraft, interplanetary spacecraft. It's the size of a school bus, stands 21 feet on its end. It was 6 metric tons at launch. More than half of that was fuel. It carries on board 12 scientific instruments on the mothership, and then it also carries a probe, an atmospheric probe that will be deployed to Titan, its largest moon, to Saturn's largest moon, and this alone carries 6 scientific instruments. I'll get to the Huygens Probe later. It has a monolithic antenna. I guess the lesson was learned with Galileo. This is not an antenna that can fail to open. It is permanently open, and the whole spacecraft has been functioning beautifully ever since launch. This is a long boom on the end of which is a magnetometer to measure magnetic fields. It is put on a long boom so that the magnetic environment of the spacecraft itself does not contaminate any measurements of external magnetic fields. And this is like a Christmas tree. There's so many things to point out. It's, as I said, very well equipped. This is what I'm going to talk about mostly tonight. This is the remote sensing palette. The 2 cameras, which are part of the experiment that I lead, are on the remote sensing palette. They are the narrow and the wide angle cameras. But there are other instruments that measure in the ultraviolet, that measure in the long infrared, basically measuring temperature. There's a radar experiment that is conducted with the high gain antenna. There are instruments for measuring the magnetosphere of Saturn and particles and fields and so on. It is designed to conduct, as I said, a very in-depth investigation of the Saturn system. Part of the reason why Cassini is going to be so successful is that it is an orbiter. And the mission design is an enormous undertaking. It was so heavy at launch that we couldn't get it directly to Saturn. So we had to loop it around the solar system. It had to fly by the Earth once, by Venus twice. Actually, it went in the opposite order. And then, of course, by Jupiter in order to give it enough momentum so that it could get onto Saturn, bearing in mind that the object of the exercise is to get to our destination as quickly as possible so that those of us who are involved in the mission are still alive by the time the spacecraft gets there. And so when we get to Saturn, here on Earth, it'll be June 30th. The spacecraft is going to be placed into orbit, and this is done by throwing the engines in reverse, so to speak. The main engine is burned. It slows the spacecraft down. That's when most of the fuel that Cassini carries will be expended, and the spacecraft is basically will fall into Saturn orbit at this point in time. This is a unique period of time for those of us who are interested in planetary rings. It is the closest we get to Saturn's rings. We are skimming over the ring plane by something like 10 to 40,000 kilometers. That is exquisitely close. And so for years, the scientists have been clamoring and arguing with the engineers to allow us to orient the spacecraft in such a way that we could have the remote sensing instruments pointing downwards, gathering measurements as we cruise like a cruise missile across the rings. Other experiments measuring magnetic fields wanted to orient the spacecraft in a different direction. It's been quite a negotiation, I guess is the politically correct term to use. But finally, we are going to be allowed to do this. We are skimming over the dark side of the rings. It's not the most ideal situation in which to make measurements, but nonetheless, there is the hope that we will be able to see in our images features in the rings that we believe to be there. The rings are countless ice particles. I'll say more about that in a minute. But they are not necessarily all randomly oriented. In the outer portion of the rings, the A ring, the outermost ring, we believe that the particles are in fact, they form these transient wake-like features where they are dense in certain areas and their numbers are more rarefied in others. And these are transient. If I could show you a movie of these things, they form, they break up, they form again. And it's basically due to the self-gravitation of the particles themselves. And so we are going to be taking images, just only a few images of the A ring where we believe this occurs. The resolution won't be, it won't look like this, okay? Our resolution is about the distance between these wakes, and it may be successful, it may not. But nonetheless, it is the only opportunity we get to do this sort of thing until, in fact, we sometime in the future, hopefully in my lifetime, send a Saturn orbiter back to Saturn and actually hover above the rings to examine how they interact. So this is going to be a very unique moment in the Cassini tour. After this moment, after we're in orbit, then the spacecraft will be in orbit forever. Okay, we don't take it out of orbit. It doesn't come back home. And we, through various gravitational maneuvers, sending the spacecraft very close to the largest satellite, Titan. We use Titan as the gravity assist body, and we can crank the orbit up. We can enlarge the size of the orbit or shrink it down. And the point here is to put the spacecraft in a variety of geometries with respect to the targets in the Saturn system so that we can view the atmosphere, we can view the rings, we can view the satellites, we can view the north poles, we can view the south poles, and so on. So we have the spacecraft often in equatorial orbit so that it can fly very close to the icy moons. We crank it up so that it's in a vantage point to look down on the rings or the poles of Saturn and the other satellites. And so this is what it looks like from above, and this is what it looks like from the side. This is what we are anticipating doing over the course of 4 years. And I will say that, I said it already, it deserves mentioning again. It is an enormous undertaking. We will be conducting 82 satellite flybys. Okay, we are going to be flying close, very, very close to some of the moons in the Saturn system. In some cases, as close to the surface as the space shuttle when it's in its highest orbit is flying above the surface of the Earth. My hat off to the optical navigation people at the Jet Propulsion Laboratory. They have a lot of experience in this. We don't anticipate that they're going to crash it into anything, but it will take some skill to execute this tour. The tour of the Galileo system wasn't nearly this challenging. There were 4 Galilean satellites, but here there are a dozen or more satellites that we want to image. Okay, so this is one of the other reason why the Cassini will be such an enormous success, because we're going to dwell there, we're going to hang out and gather information during the course of many years. The nominal mission length is 4 years. We're anticipating it could go on for a long time. Oh my God, what is this? Is superstition triumphing over science and technology. So I think I know how to do this. Hello, there we are. Okay. All right, so what are we going to see? First is the atmosphere of Saturn. Saturn is colder than Jupiter, and so the clouds in its atmosphere are lower in the atmosphere relative to the atmosphere of Jupiter. It means there's more overlying haze. It means that the features there are harder to see. Nonetheless, we don't anticipate we will have any problems. We have a beautiful camera with a very large dynamic range. We can contrast enhance in order to see features. And why do we want to see these features? Features like this are the kinds of features, for one, that scientists measure the motion of to determine wind speeds. And the wind, from Voyager, we know that the winds at Saturn are enormous. The equatorial jet at Saturn is something like 1,200 miles per hour. Okay? It's the windiest place, along with Neptune, it's the windiest place in the solar system. And we don't know yet why the winds on the giant planets are this energetic. It does not follow the pattern you would think with distance from the sun. The deposition of sunlight and the energy of sunlight is not the key factor here. And so we are in pursuit of the answer. What drives the winds on Saturn and on the other giant planets? We also wish to know if the banded nature of the giant planets is a superficial thing, or does it go deep? There's no surface on Saturn. There's no surface on Jupiter. They're banded planets. How deep does it go? Okay, and these are questions that scientists hope to answer, all with a view towards trying to understand as well, having a point of comparison with the meteorology of our own planet. The mission design for studying the planets, the atmosphere includes, in our case, in the case of the imaging experiment, repeated images in various filters in order to make movie sequences. We've done this already at Jupiter. If you visited the Cyclops website, you know we have movies of the Jovian atmosphere. We'll be doing the same sort of thing with the Saturn atmosphere. And we have a little preliminary movie that we've released already. I'll show you that at the end. There's also this very elegant experiment called an occultation, where the telemetry signals of the spacecraft are occulted by an object like Saturn as the spacecraft disappears behind the planet as seen from the Earth. And the way that the signals of the spacecraft are attenuated as they pass from the vacuum of space through the atmosphere and then, of course, to the densest part of the planet, gives you information about the density of the atmosphere and the pressure profile and so on. It's a very elegant experiment. It's also conducted with planetary rings, so we can measure the positions of the ring features to very high precision. We will be conducting several of those during the Cassini tour. So hopefully we'll have some answers about what makes the Saturn atmosphere tick. Then, of course, there are the rings. The rings of Saturn are what makes Saturn so alluring, what makes it such an object of beauty, and what makes it the icon among planets. The rings are 1 light second across, 280,000 kilometers. They would fit neatly between the Earth and the Moon. They are gigantic, and yet they are paper thin. They are only about 10 to 20 meters thick, probably no thicker than, on average, no thicker than the height of this room. Okay, they're a very equilibrated system, lots of particles, ice particles, colliding, losing energy as they collide, and they've all settled down. The ring system itself traces out the plane of gravitational equilibrium around Saturn. It is very mathematically precise. Let me familiarize you with the ring components, because I'll say more about these. The outermost ring is the A ring. This is the ring that we think has those wake-like features I showed you in a previous diagram. The A ring is separated from the B ring by the Cassini division. It's a nice little historical footnote that when the engineers at I guess it was Ames Research Center, were planning the Pioneer spacecraft, which was actually the first spacecraft to fly by Saturn, they were entertaining sending it through the Cassini division. But we found out later that would have been a terrible idea, because the Cassini division is not entirely empty. The B ring is the densest part of Saturn's rings. And then there's the very low, optically thin C ring. These are the major ring elements that were visible from the ground. Then there's the very even more diaphanous D ring here, and there's other diffuse rings outside of the main rings, and then of course there's the very narrow F ring. As I said, the rings are countless bodies ranging in size from the kind of powdered snow you might ski on in Utah all the way up to boulders the size of houses. This is probably, we still think, what the ring system, the large rings, ring particles look like, about 10 meters or 20 meters across. They may, in fact, be the agglomeration of smaller particles and interspersed with more numerous small particles, all in a very flat plane. They are screaming around Saturn at 10, 20,000 kilometers, miles per hour, but yet they gently jostle each other at less than a centimeter per second. It is a very equilibrated system. Most of the particles are on mostly spherical orbits, but it is those features in the rings where the particles are on eccentric orbits that interest us as well. I will say that in being a very flattened disk system consisting of many particles, there are similarities between the rings of Saturn and the protosolar nebula from which the planets formed. There's no gas in Saturn's rings. Here there's solid material and gas, but nonetheless, we believe now that there are processes ongoing in the rings of Saturn that did take place in the disk of dust and gas, from which the planets formed, and even reaching farther in size, some trillion times larger, even going out to the spiral galaxies. There is commonality between the spiral galaxies and what we find in Saturn's rings. In fact, the mathematics for understanding spiral structure in spiral galaxies was basically co-opted, changed in some minor ways, and applied to Saturn's rings to predict that Voyager would find density waves, spiral waves in Saturn's rings, and lo and behold, we found density waves. So this is one of the reasons for having such optimism in what Cassini will find at Saturn, and how broad a reach the results that we will find will have in importance in other communities that are interested in disk systems. Some of the questions that we are interested in answering in Saturn's rings are those that a casual observer might ask in looking at Saturn's rings. Where did they come from? How long have they been there? How long are they going to stay there? How fast are they evolving, if they're changing at all? These are some basic questions that we scientists don't yet have answers to, and those are some of the questions that we hope to answer when Cassini arrives there. This is the A ring, the outermost A ring. Here is the Yankee Gap. It's a nearly empty gap. There's another little gap there, the Yankee Gap. The A ring goes from about here outwards. Almost all the features, in fact here, all the features that we see okay, are explainable by the perturbations of a distant moon. Okay, this is the gravitational excitation of the orbits of the ring particles causes these features. If you could look at them more closely, they look like very tightly wound spiral waves. Okay, some of them, well, we'll look even more closely at the Yankee Gap. Okay, the Yankee Gap here. Okay, there's that little gap, the Keeler Gap there. We're looking now even more closely at some of these features. You could see that they have multiple components. This is really just a very tightly wound spiral wave where what is spiraling actually is the particle number density in the rings. In some places it's dense. You move a little further out, it gets more rarefied. A little further out again, it gets dense again because of the perturbations of a distant satellites, distant moons. We feel pretty good that we're able to at least understand some of the characteristics of the structure. We don't understand everything. We don't really have a theory that tells us precisely how much angular momentum is being exchanged in the interaction between the moon and these waves. But what we do know tells us that the orbits of the moons, which are having this interaction with the rings, should be changing. And that would be a beautiful measure of how fast angular momentum is being extracted from the rings and how fast the rings are evolving. And so that is one thing that we're very excited about, the possibility that we could go there, find changes in the orbits of the satellites between the Cassini epoch and the Voyager epoch 23 years earlier, or just perhaps even see things change while we're there for a period of 5 or 10 years or whatever that will be. This is a special circumstance here. This is the Yankee Gap. It is being kept open by the small satellite Pan, which is only about 20 kilometers across. Now, that may sound counterintuitive to you because you've been taught that gravity is attractive. And here we have a situation where you have a moon that is pushing material away from it. Well, that's because gravity is attractive when we have only two bodies, but when you add another body, okay, you add, for example, the planet Saturn, and the two bodies are in orbit around Saturn. Okay, and this is even more true if you have a whole system of particles, like a disk of rings and a satellite, all in orbit around a planet. You have the very counterintuitive result that you can actually get a satellite pushing material away from it. And this actually turns out to be a wonderful analog for what some people think is the way that Jupiter, a planet like Jupiter, growing in the protosolar nebula, truncated its own growth. It was there collecting mass, collecting gas, and so on, growing until finally it got so big it pushed away any remaining material, and that determined how big it got. So again, what we are going to be able to find by recovering Pan, measuring its orbit, finding out if it's eccentric or it's circular, understanding the exchange between the satellite and the material around it, will be useful in understanding how protoplanets grow in disks of material, and will also help us interpret the observations that are being made seemingly all the time now of planets growing in exosolar disks around other stars. Okay, here is the B ring. We're moving in now. We were looking at the A ring. Now we're looking at the very dense portion of the B ring. It looks here like there's lots of gaps. There's no gaps in, there are no gaps in this picture. It's just that we have contrast enhanced. We've stretched the picture in brightness levels, sending the not so bright stuff to black and the brighter stuff to white, just to point out the detail. This is the densest portion of Saturn's rings. There are features here down to the finest level that we saw with Voyager, which was about 4 kilometers. Okay, the smallest feature we saw in Saturn's rings was something like 3 miles. Okay, we're going to improve that by about a factor of 3 with Cassini, so we will be able to see smaller structures. But this whole region here is a puzzle to us. We don't really understand now what causes the structure. This is not a place where there are perturbations from satellites. Obviously, these are structures that can be self-perpetuated in a ring system. The ring system is dynamic. There's angular momentum flowing out. Even if you left it to itself, angular momentum would flow out through the ring and the ring would spread. And so we want to understand those processes, and hopefully we'll do a better job than we could do with Voyager in examining the very densest portions of the B ring. We'll do this, as I said, with finer resolution images, and there will also be stellar occultations that will be conducted that will allow us to penetrate this thick portion of the ring. Okay, so next comes the satellite system of Saturn. I don't know any longer how many satellites there are. There are satellites being discovered all the time now around Jupiter and around Saturn. These new satellites that are being discovered are in the very, very distant region, tens of millions of kilometers away from the planet. The ones around the planet, any new discoveries is probably going to be up to us to discover. So we are going to be on the lookout for new satellites. Any satellites we find are going to be small because Voyager would have found them already. But there are about a dozen satellites that we are interested in examining up close with Cassini. They range in size from 20 kilometers, the Pan in the Yankee Gap that I mentioned, all the way to Titan, which is Saturn's largest moon, which is as big as the U.S. is across. Insofar as this collection of bodies in the inner Saturn system are all basically in a plane, they're all orbiting an object where most of the mass is, where they apparently formed out of the material, the Proto-Saturnian nebula. In these regards, the satellite system of Saturn can be considered a miniature solar system. And so studying it as a whole, examining compositional gradients across it, examining bulk density gradients across it, understanding the tectonics on the features, the geological histories on the features, what were the thermal environments of the satellites, each satellite at the place where it formed. All of this will help us understand the processes that gave rise to the solar system and the planets in our solar system themselves. And it will advance our understanding of the geological processes and the thermal histories of the bodies themselves, obviously. Will give us an unprecedented view of their geological evolution. Cassini is going to get on these bodies the same resolution that Voyager got, except globally. Okay? Voyager, the best resolution Voyager got on some of these satellites was only about 1 kilometer. We will, in almost all cases, cover each satellite globally with that kind of resolution and better. We'll probably get down to 200 meters per pixel globally. And the mission design, as I said, will allow us to search the system for new satellites. There will be 45 flybys of Titan alone. I'll say more about that. 7 very close flybys of the icy satellites. These are the ones we are skimming over the surface. And 30 sort of close flybys, but better than we were able to do with Voyager. And let me say that, let me describe to you what will happen. Imagine, I said to you already that Voyager spent a very brief period of time in the vicinity of the Saturn system. It just flew by, okay? And these satellites are tidally locked, okay? They always present the same face to Saturn. And some of them take days to go around, tens of hours or days to go around Saturn. So if Voyager flies by and gets close to any of them, it only really saw up close 1/2 of each of these satellites. We don't have a good view or a good detailed view of the other half of the Saturnian satellites. And imagine if you were on a spaceship approaching planet Earth. Okay, you've never seen Earth before. And you're an alien, you're approaching our planet, and you make your point of closest approach above French Polynesia. That's Tahiti. Okay, and I encourage you to go home and do this. Take a globe of the Earth, hold it at arm's length, put Tahiti under your nose, and you will notice that the hemisphere that you are seeing is almost entirely water. Okay, there is a strong hemispherical dichotomy on our own planet. Half of it is water, all the continents are on the other half. So if you were an alien making your approach to planet Earth on the trajectory I just described, and that was the closest view you ever had, you would come away with a very incomplete picture about what the geological processes and geological history of the Earth were. Same with Voyager's encounter with the Saturnian satellite system. We only really got to see half. So in this regard, Cassini is going to be like a reconnaissance mission. We are going to see things we hadn't seen before, see them up close, and see them with very great precision. What does very high resolution do for you? Here is a picture, a series of pictures of Europa. Europa is the very exciting target or satellite in the Jupiter system that is believed to have a subsurface ocean. Voyager, the best Voyager did was an image like this, about 2 kilometers per pixel. Okay, and we saw these stripes and these features that were crisscrossing. It was very mysterious. People didn't know what they were. They didn't know topologically what they were. Are they highs? Are they lows? Are they grabens? Are they mountains? What are they? We didn't know. Galileo, of course, orbited Jupiter in 1995 and returned some very startling pictures. You can see when you go from 2 kilometers a pixel to about a half a kilometer a pixel, well, you start having the prayer of figuring out this feature overlies that feature, and you can see more detail, and you start developing a clearer picture of what has preceded what and so on. But it's not until you get down to 35 meters a pixel. Okay, this is a picture, at least if this were a Cassini picture, this would be, let's see, is that right? I was going to say you could walk across it in a day. That would be 35,000 meters, 35 kilometers. Okay, well, maybe 2 days. Okay, you could walk across. It's starting to get very familiar. You can recognize where the sun casts shadows. You can measure heights. You can understand the tectonics. Okay, and it was going to this kind of resolution that the scientists on the Galileo project were able to deduce that Europa probably at one time, maybe even today, has a subsurface ocean. And so it will be with Cassini. We are going to get some very high resolution pictures of the Saturnian satellites, and we'll come away, I'm sure, with some very exciting impressions about what their geological history has. Some of the highlights for studying the Saturn satellites. Here is Mimas, the Death Star satellite. It's about 400 kilometers across. Obviously, it got whacked really big time, okay? The object that collided, the projectile that collided with Mimas and created this crater, which is something like a quarter of its size, came very close to smashing Mimas to bits. And we only have to look at objects like this with visible surfaces to see that there was a time, billions of years ago, when a great many bodies carrying enormous amounts of energy were careening around the solar system and smashing headlong into the planets and the satellites as they were forming. And these colossal collisions did a great deal to build and sculpt the solar system that we see today. These collisions were responsible for, first of all, allowing the planets to grow up to their present size. For example, comets, large comets, probably made up the outer planets Uranus and Neptune. Okay, and a modern-day example of a comet colliding with a planet is Comet Shoemaker-Levy 9. Collisions were responsible for tilting Uranus on its side. They were responsible for creating the moon, we believe, when a Mars-sized object collided with the Earth and basically stripped off a good deal of its outer layer, threw it into Earth orbit, and from there it coalesced to form the moon. Collisions smashed up small satellites, like it almost did here to Mimas, and it also probably created ring systems. One of the ideas about where rings came from is that there was a progenitor body, maybe a couple, in orbit around Saturn, and a projectile came, smashed it up, and instead of forming again back into a planet, the material was close enough, it was prevented from doing that by Saturn's tidal field, and so it turned into a ring system. And perhaps collisions brought prebiotic organic material to the Earth. That is another popular idea of how life might have arisen here, is that the organic material from which life arose was delivered from afar. And as you know, a collision with a comet wiped out the dinosaurs, which cleared the way for the eventual development and successful evolution of the primates, of which we like to believe we are the culmination, which is to say it would have been difficult to invent calculus with a Tyrannosaurus rex breathing down your neck. Collisions have done a lot, and in fact, one of the studies that is done with imaging data of planetary bodies is to measure the density of craters and measure how they're distributed, the numbers of them are distributed across the surface, find out which areas are less cratered than others, and construct the series of events, the geological history of a planet that way. We can do this, in fact, with a body like Enceladus. Enceladus is, I predict, going to be the Europa of the Saturn system. Might possibly be. It has enough peculiar characteristics, it being completely white, so something is probably actively keeping it white. And it's slightly out of round. It could possibly be that there is a subsurface ocean here. We don't know. But you only have to look at the surface here to know this area here is not cratered, this area here is. And likely what happened is that the same crater population that cratered this surface cratered this, and then later on material was extruded from the inside of Enceladus onto the surface at some later period of time. So this is therefore a younger surface than that. And it is this way that scientists piece the geology of a body like Enceladus together. So we will be doing this in spades with the images that we collect from the surfaces of the satellites. And then finally, not finally, but another exciting target of Cassini is going to be Iapetus. This is our solar system's yin-yang moon. Half of it is as nearly as white as snow. The other half is as black as the blackest material we have in our solar system. I said that some people believe that materials from which life arose were delivered to the Earth in the form of comets long ago. If so, then a study of a body like Iapetus is likely to be very intriguing. Studies of the composition of the dark material in Iapetus since the days of Voyager have indicated that it seems to be a mixture of organic material plus hydrogen cyanide and water ice. Hydrogen cyanide is an important prebiotic molecule. And it seems, of course, that, I shouldn't say of course, it seems like the comets seem to be made of the same stuff. So did this stuff get delivered to Earth? Is that where the organic material from which life on Earth formed came from? Another question is, how did the dark material here on Iapetus get there? Was it deposited from the outside, or was it extruded out onto the surface at a time when Iapetus might have been warmer? Questions that are unanswered right now, and we hope to have the answers soon. Anyway, exciting times in the study of Saturn's satellite system are about to begin. And then, of course, I saved probably the most tantalizing for last. Titan is Saturn's largest moon. It is the size of Mercury. If it were put in orbit around the sun, we would have called it a planet and have had lots of spacecraft missions to it by now. It alone would make the journey back to Saturn worth the effort. For 50 years, we have realized that in its atmosphere is contained the simplest carbon-bearing molecule, which is methane, a carbon and 4 hydrogen atoms attached to it. And in the 1970s, before Voyager got out there, simple organic compounds, other organic compounds were found. So even back in the pre-Voyager days, scientists were very excited about the possibility of Voyager getting to the Saturn system, taking a close look at Titan. Unfortunately, the best that the imaging experiment did on Titan is this. Okay, it turned out that the absorbing and scattering properties of the Titan atmosphere were exactly mismatched to the capabilities of the Voyager imaging experiment, where it does become possible to see down through the atmosphere to the surface of Titan. That's where the Voyager camera became blind. So it is going to be left up to Cassini to complete the picture of Titan and determine what exactly is under the haze on Titan. However, Voyager was successful in that its spectrometer experiments confirmed the existence of the organic compounds that were found from the Earth, and found others that were more complex, like propane, diacetylene, methylacetylene, monodeuteраted methane. There's going to be a quiz after this. And then three nitrogen-bearing compounds, including hydrogen cyanide. Again, HCN is an important prebiotic molecule. It also found that Voyager, the other experiments besides the imaging experiment, found that the dominant constituent in Titan's atmosphere is molecular nitrogen, just like the Earth's. It also found that the pressure on the surface of Titan is comparable to the Earth, something like 50% greater than what we have here on Earth. And it turns out, after all is said and done, that its atmosphere, Titan's atmosphere, though it is not identical and it's different in some important respects, is more similar to the atmosphere of Earth's than any other body in the solar system. In its physical characteristics, its thermal structure, in its atmospheric processes, it has stratospheric heating, it has greenhouse gases, and it probably has condensation and rain. Very likely there's a liquid reservoir on its surface. Methane, ethane oceans are possible on the surface of Titan. So it could have geological features that arise from the interaction of water with the surface, rivers, cataracts, shorelines, wind-driven waves, things that are very familiar but yet out of very unfamiliar materials. Are you getting goosebumps yet? Okay, dissimilarities. There are some important dissimilarities. It is very cold on Titan, and because of that, there's no liquid water. Okay, so this is not the early Earth. It's similar to the early Earth, but not the early Earth. And I say early Earth because there's no oxygen. There's no free oxygen on Titan. And so it is believed to be similar to the Earth. It's the atmosphere that the Earth had prior to the emergence of life. Oxygen, as you know, came from photosynthesizing bacteria. Nonetheless, there's significant insight into the conditions that prevailed on the surface of the Earth in studying Titan. So in some sense, we have the opportunity to travel back in time and study things that might have gone on the surface of the Earth. Cassini is going to be the first in-depth characterization of Titan's surface and atmosphere. As I said, we fly by the object 44 times. Because it's such an intensely interesting object, there's been a lot of negotiation again among all the instruments on board the spacecraft. There are instruments like the remote sensing instruments, of which the cameras are part, that want to look at the surface, look at the atmosphere, take images, take spectra. There are investigations that want to look at stellar occultations of the atmosphere, as I described already, to discern the variation of the pressure profile and the density with latitude. There is one instrument called the ion and neutral mass spectrometer that, in fact, on our very close passes of Titan, we are basically passing through the upper atmosphere, and this instrument will scoop up the atmosphere of Titan as we fly by, measuring its chemical composition, the very place where we think methane is being broken apart by sunlight to form free hydrogen and then carbon polymers, which then rain down as organic goop down onto the surface. And then finally, there's also a radar experiment. As I explained to you, the radar works at very long wavelengths and has no trouble whatsoever seeing the surface. Okay, it showers the surface with electromagnetic radiation, and then it collects the reflected light back into the high-gain antenna, and then back on Earth. All this information is cleverly put together to create a synthetic aperture radar image. Will look very much like the SAR, the SAR images that were produced of the surface of Magellan. This experiment will cover something like 20% of the surface of Titan in this way. And then probably the most exciting investigation of Titan will take place when we deploy in December of this year. I think it's on Christmas Day, in fact, we deploy the Huygens Probe. This is a device, a probe, that has been built by the Europeans, although there are some American instruments on board. There are 6 experiments to measure the characteristics of the atmosphere, the amount of sunlight in the atmosphere at any one level, the scattering from aerosols, the tracking of the probe as it descends itself will give us a measure of the Titan circulation. And this takes place over the course of 2.5 hours as it descends. It makes all these measurements. And then finally, the most thrilling part, at least from my point of view of this, is that when it breaks through what we think is the lowest cloud layer, although we don't really know, it's just what our models tell us, but when we think it's free and clear of any obscuring clouds of the surface, a flood lamp is thrown onto the surface. This floodlight is specially designed to fill in the regions of the electromagnetic spectrum where the atmosphere above has absorbed, to create a spotlight which is as white, as spectrally white as possible, so that the spectrometers on board the descending probe will measure the light that's reflected from the surface, and with it presumably will be imprinted on it the chemical signature of the Titan surface. So this is going to give us our most detailed view of one locale on the Titan surface. If it happens to land in liquid, there is a package, a scientific instrument package on board that should be able to measure the acoustic properties of whatever it falls into. So, and then after this happens next January, the rest of the tour proceeds, and all the observations I just described to you will go on over the course of time. We hopefully will finally unveil Titan and understand its geological history. It's perplexed us for quite a bit of time because we don't know what's there. You can imagine imaginations run wild. We will characterize its surface, understand its physical properties, its geographic variability from ground-based observations and Hubble Space Telescope observations. It is clear Titan has a heterogeneous surface, and so we will have images of its surface, presuming that we are successful in seeing down to the surface, and we think we will be because we have specially designed our filters to fit just in exactly those spectral regions where we know ground-based observations have been able to see to the surface, so we're very hopeful about this. We will map the surface of Titan to something like 200 meters resolution, and in some cases we will have very fine resolution, as I showed you before, tens of meters per pixel. We will understand if there's craters on the surface. We'll be able to understand or look for their morphology. Are they relaxed? The morphology of craters tells you the properties of the material that the crater was made in, the mechanical properties. Will there be tsunami deposits from impacts into the seas on Titan? What kind of interaction between the surface and fluid will we see? Methane, I told you there's methane in the atmosphere. We don't know how the methane gets there. It is the greenhouse gas on Titan. Titan, in having an active greenhouse with methane in the atmosphere and possibly methane in liquid form on the surface, is closer to the greenhouse of Earth than is Venus. In the case of Venus, the greenhouse has run away. There's no liquid on the surface anymore. On Titan, we could have methane on the surface and in the atmosphere, just like we have water, which is in fact the main greenhouse gas on Earth, on the surface and in the atmosphere. There is much to learn by studying Titan. In any case, I hopefully have convinced you that Cassini is a mission of enormous scientific scope, will have very far-reaching consequences well beyond the study of the Saturn system itself, should tell us about the origin of planets and satellites, about the solar system as a whole, may provide the opportunity to study processes involved in the run-up to life's origins here on Earth, and may provide information on processes involving greenhouse gases and even global climate change. And beyond the solar system, it should offer important sources of information for the study of dynamics and evolution of other celestial disks, like spiral galaxies and disks around other stars, and the origin of other planetary systems. It is also a mission of enormous visual delights. And if you've been watching over our shoulders, like we have invited you to, and gone to our website, you know what Cassini has already found at Jupiter and what we're finding as we approach Saturn. And even for people like myself who are supposedly experienced at this, we are amazingly startled at the clarity and the precision of the images that have been returned. This is just a lovely image of Io floating above the clouds of Jupiter that was taken on January 1st, the year 2001, making our closest approach to Jupiter, showing tremendous detail, and I want to say natural color. I am committed to making natural color images wherever possible, to give all of us the impression of what it would be like actually to be there to the extent possible. And then, of course, in October of 2002, we made one of our first sightings of Saturn, looking here very, very distant and aloof, just waiting for us to arrive. And then in February of this year, we started collecting data on approach, seriously collecting data almost daily on approach to making our final approach to Saturn. Data started to arrive here on the Earth on February 9th, which I have to say is the 40th anniversary of the arrival of the Beatles here in the United States. And the coincidence of those two events just proves to me that I lead a charmed existence. So they are looking over our shoulders too. And here's a little movie we made of Saturn in the deepest methane band that we have available to us. It's a long exposure, so long it completely saturated the rings, but points out the winds at the equator of Saturn. It goes kind of slow because my laptop is not very fast. But anyway, we'll be making more of these as we get closer. This is a result that we released last week. This is remarkable for us that we're still so far away, and we were able to capture two storms about 1,000 kilometers across, merging on Saturn. This is the second time that this has been observed on Saturn itself. We don't understand what forms these storms to begin with, but it seems that the way they die is to merge. They cannibalize one another. So there'll be more of this, I'm sure, as we study the atmosphere. We're already zooming in on the rings. This is a very contrast-enhanced image to show clumps in the F ring. These were discovered by Voyager. They even were seen from the Hubble Space Telescope. We don't know what causes them. The F ring is in a very psychotic region around Saturn. It's kind of in that midway region between being a complete ring to being something that might want to go back to forming into a satellite. And it is between two satellites, and I'm incredibly excited, and we're getting closer, and we finally have sighted these two. And then, of course, there's just the beauty, as David said, of Saturn, Saturn itself, which never ceases to move me. Anyway, this is just, of course, the beginning. It's just the hors d'oeuvre. The feast is yet to come. On a more personal note, I want to say that I've been giving this same talk now for 13 years. And for the past 23 years, our views and our impressions and our recollections and our understanding of Saturn and its environment has been largely provided by the images that were returned by Voyager during the 1980s, and nearly a quarter of a century ago. And I'm enormously sentimentally attached to Voyager. It was probably the greatest mission that was ever conducted, but that is all about to change. And the time is close at hand when we are going to cross over the threshold, and when new sites and new places that we've never seen before and new details on places that we have seen before will become available to us. And after 13 years of preparation, it's good to know it's only a few months away. It is exploration at its finest, and don't miss it. Thank you.
We have time for a few questions. If you hold your hand up, we have microphones, and either side, and I've been instructed that we have to do one side and then the other side so it will be balanced and fair. So let's start.
Excuse me. Is that like Fox News?
It's Fox News at its best.
Yes, wonderful talk. Thank you. I was wondering, have you had any thoughts that the spacecraft itself might have?
Okay.
Oh, here.
Oh,
have you had any thoughts that the spacecraft itself might have gravitational effects on the rings?
Oh, no, not a chance. It's first of all, it'll never get that close, and it's tiny compared to anything else.
Question over here?
How big was the Yankee Gap?
The Yankee Gap is, oh boy, oh shoot. Well, I got two numbers on the brain. It's either 150 kilometers across or 300 kilometers across, so something like that.
What would you like it to
Is this a quiz? I bet I have the answer. Oh, it's 150 kilometers across. So if this was multiple choice, I'd have 50% chance.
All right. Question over here.
The Huygens craft going down to Titan, is it designed to survive the landing, or is it as soon as it reaches the surface, it's done?
It just depends what it lands into. If it lands on something very, very, very hard, like solid ice, chances are it won't survive. But if it lands in snow or the Titan equivalent of snow, if it lands in a fluid, it might survive. The length of time it will collect data, however, is going to be determined by the length of time it's in communication with the mothership. And it takes 2.5 hours to get down to the surface, and if it survives, I believe we have another half hour, before the mothership disappears over the horizon. And by the time it comes back again, the batteries are long dead.
Will it float?
Oh, yeah, it will likely float. Yeah, it's shaped so that it should float. I mean, if we understand what's going on in time.
Well, I'd also like to say appreciate the lecture, but I would like to ask just a very simple-minded question. Why is it that there is one ring, why not multiple rings or maybe a shell? I mean, what got all this ice to form this very discrete, elegant ring instead of a whole series of rings or maybe a shell?
A system like Saturn's rings, which is multiple particles, all in orbit, independent orbit, but colliding with one another. If there were no moons around, nothing else around, just the sheet of material in orbit around Saturn, where it, let's say, is right now, it would spread, okay? Because angular momentum is, because of the collisions, angular momentum and energy is being exchanged among the particles, and it flows outwards generally. I mean, not generally. It flows outwards in a disk like Saturn's. So left to themselves, the rings would spread to the point where they're not interacting with each other anymore. It might even be like the asteroid belt. The collisions are so infrequent, what I just described to you doesn't happen anymore. Okay? Okay, that's a different situation. Let me complete the first thought. So the first thought is that where there are divisions, and this is going to be a part answer because we don't know the full answer, but where there are divisions like the Cassini division or the Yankee Gap or even the outer edge of the A-ring itself, those divisions and boundaries are determined by the interaction with moons. Okay? There are some boundaries, though, that don't seem to be determined by gravitational perturbations with moons, so we don't have the full answer. As far as why it settles down that way, that is the normal outcome of a system of particles and gas and so on. If you imagine a cloud around Saturn and the material is orbiting, colliding, and so on, it will normally settle down into the plane that is perpendicular to the spin axis of the body. Okay, and it's because spin makes a planet like Saturn slightly oblate, and it singles out. Oh, God, I'm violent here. Singles out a particular plane in space, and the particles all tend to gravitate there. It's the place of minimum energy, actually. That's why they go there.
All right, let's take 3 more questions. Any on this side over here? Let's take one over here then.
I'm sure that there'll be enough light underneath all those big clouds on
Well, there are some pretty sophisticated models of what the Titan atmospheric structure is like. And we can already see when we look at particular wavelength regions. I guess I didn't give you this whole story. I said that the Voyager camera was blind where it started to become possible to see down to the surface. And you can see down to the surface as you go to longer wavelengths and you look in between the regions where methane in the atmosphere is absorbing. So these are like little windows between the methane absorptions where the only thing that is preventing light from getting down and getting back is scattering by the haze. It's not gaseous absorption, it's scattering. It's like a fog, okay? But nonetheless, as you go to longer wavelengths, that scattering becomes less important or less dominant. So at the longer wavelengths, we have, from the ground and from the Hubble Space Telescope, we have been able to see down at the surface. So the probe, the Huygens Probe, our cameras, other instruments on the Cassini spacecraft, I mean, the scientists have gotten smart, believe it or not, and we've designed these instruments so that we can see down into those spectral regions. So the probe, I don't think, is going to have problems. If we can see from above the atmosphere, they'll very likely see while they're in the atmosphere.
Question on this side over here anywhere? One over there?
You said that the moons were, or at least one of the moons was.
I'm sorry, where are they? You are, okay.
You said that at least one of the moons, I don't remember which one, was transferring angular momentum to the rings. Is that a process that we could trace backwards in the past to suggest what its orbit would have been in the past? And if it continues, is the moon at some point going to crash into the planet in the future if it loses enough energy?
Okay, first of all, you got it backwards. So or maybe I said that and I didn't mean it. It's the other way around. An external satellite will withdraw angular momentum from the ring. So in doing that, it moves further out. And yes, the people have played this game of figuring out, okay, well, let's say they started off coincident, okay? You work it backwards. How long ago was that? And that is one of the ways that people get at the life, how old the rings are. And that gives you something like a few 100 million years. Okay, there are other avenues that people, lines of argument or whatever. What am I trying to say? Lines of evidence that people use to deduce ring lifetime. They all seem to be, right now anyway, around a few 100 million years, which means, if that's correct, during the days that dinosaurs roamed the Earth, there were no rings around Saturn. So, but we don't know. We'll hopefully find out when we get there.
Question over here. No, the man with the microphone.
Yeah, right here. Hello. Hi. You mentioned that the orbit's going to change before it becomes solid. Is that
the orbit is going to change
of the satellite? Didn't you say you could make it bigger and smaller?
Oh, you mean cranking up the size of Cassini's trajectory around Saturn? Yes.
Is it going to pass through the rings when it does that? Or?
Oh God, we hope not.
Okay.
I mean, there has been a lot of effort to make sure it doesn't go through any ring. You would be surprised a tiny, tiny, tiny little BB-sized thing going at 5 or 6 kilometers a second could kill us.
Destroy it. Is there a lot of junk that could hit it, or?
Well, again, we hope not.
Oh, geez.
Okay, one more question right here, and then we're going to wrap it up before Carolyn loses her voice.
I thought that you said that the primarily Saturn was made of ice and water. And that being the case,
I'm sorry. Say that again. You said.
I thought you indicated that Saturn was made primarily of ice and water. And if that is the case, how can you have magnetic fields? And also, you said at minus 3 degrees Fahrenheit, ice and water acted differently than it does here. What differences are there?
Okay, let me see if I got this. First of all, I hope I didn't say Saturn was made out of ice and water. It's mostly hydrogen, and hydrogen under tremendous pressure. The electrons get stripped out of from the protons. It becomes an ionized plasma. And when ionized plasmas move, they can create magnetic fields. At least that's the going idea. It's a dynamo inside Jupiter and Saturn and so on that make magnetic fields. However, Uranus and Neptune also have magnetic fields. And I forget now, I think it's Neptune's case, the source of the magnetic field is 2/3 of the way out from the center in the shell that's believed to be mostly water. So who knows? We don't know the answer. And I'm sorry I didn't catch the second question.
Water and ice at minus 300 degrees Fahrenheit is different than it is here on Earth.
Oh, I just meant that ice, well, for example, ice here on the Earth, glaciers flow over long periods of time, but you make them minus 300 degrees Fahrenheit, and they're like a rock. So.
Thank you very much.